So anyways, I say, tissue? I hardly know you!
That's a good one.
I know.
Oh! I left my buns in the oven.
Grab your buns. Oh! Hello, I didn't even see you there. Welcome. This is Science and Dinner with Travis and Billy. I'm Billy.
And I'm Travis.
And tonight we're just enjoying a nice meal here. I have my special top ramen with eggs and tapatio. Travis, what are you eating there?
Well, only the famous Travis Dodd rice, teriyaki, and eggs. With some sourdough bread.
And it's oh so good. But, you know what, Travis? I think there's actually a lot of science behind what we're doing here.
Really, Billy?
We're talking about heat. Heat is what gets food cooking.
Yeah, it does.
Without this heat, we'd be eating cold food. Nobody wants that.
Darn straight.
So tonight, we're going to be talking to you about the science and physics behind heat conduction. For the first part of our lesson, we're going to be talking about heat conduction with different types of materials. Basically what heat conduction is the process of heat transferring from a heat source, i.e. fire, to another object like paper or even food. Basically what's happening with heat conduction is the heat is transferring into another surface through the atoms, and the atoms are then in turn becoming more stimulated, and the atoms inside the material is moving more rapidly. And the thing that makes something more or less conductive to heat is how many free electrons within those atoms are available to move freely within each type of different surface. So something like a copper tube that I have here is a very good conductor of heat, and that is because the electrons within each of the atoms inside this metal tubing are able to move very quickly. So when heat comes into it, it's able to spread it out and just is very good for transferring heat, where something like a wooden spoon is a bad conductor of heat. So heat doesn't tend to travel through it. So when we're talking about something like cooking, for example, you're going to want to use something like a wooden spoon to get inside and like stir something that may be boiling. And that's why you have like your wood or plastic, which are good and safe for conducting heat. But if you use something like a knife, the heat is going to be able to transfer through the metal here, through the process of conduction, all the way up into your fingers, and it's going to burn you. So you don't want to stir with something metal because it's too good of a conductor of heat. And so something like silver is the best conductor of heat, and then copper after that, all the way down to like iron, etc., different types of metals. So to show this in process, I'm going to use this here candle, and let's start first with a dollar bill. Now, I believe I could do this with a lot more money, but if I had more money I might do that, but this is the biggest bill that I have, so we're just going to go with this guy. But it's just an example of how confident I am in this science that this dollar bill will not burn. I'm going to hold it over the flame for 5 seconds and then remove it, and there will not be a hole burnt in the bottom of this dollar bill, whereas if I had done it just in itself over the flame, then it would create a hole. So I'm going to hold it for 5 seconds and then remove it. 1, 2, 3, 4, 5. And it's absolutely untouched. Normally you can do this with, let's use a piece of paper here. You hold it there for a good amount of seconds, right on the flame there like that. See? It didn't catch fire or anything. There's a scorch mark there, but that's just the soot from the open flame, and I can actually rub it out with my finger pretty good, and it's still almost completely untouched. Whereas if I hold it for just the same amount of seconds, just straight over the flame, it just bursts into flames. No biggie, no danger here. But that's just an example of the science behind conduction. Whew! It's cooking in here. Now to Travis with a little bit more about conduction.
So what I want to talk about is specific heat capacity. For instance, this knife Billy kind of talked about is a very good conductor of heat. So that means it's going to have a very low specific heat capacity. It doesn't have a lot of capacity or a lot of room to contain the heat. And so, like if I basically hold it over the fire for a long time, it is going to burn me. Some of you recognize if you're making soup or something like that, and you leave your steel or metal ladle in the pot, it's really going to burn you. So you got to be careful of that. For instance, this balloon itself has a very low heat capacity. So just in itself, full of air, it's going to pop if I hold it over the flame for too long. It's gone. Now, however, we're going to talk about the high capacity of heat, or high capacity of water, and its ability to absorb a lot of heat, which also makes it a very good cooling agent for engines and different things like that. So if we actually fill the balloon full of water, the water is actually going to cool down the outside of the balloon itself in order for it to basically contain a lot of the heat. It's going to take a lot of that from it. That means the water has a very high heat capacity. So, for example, I hope this works out. It did! Okay, good. And I just got a little burn mark right there, but for the most part, the water was able to cool down the outside of the balloon so that it didn't pop. The water was able to absorb the heat coming from the flame, even though I unfortunately was holding it on the flame. So, again, kids, metal in the heat, very bad, it will burn you. Water is a good cooling agent. That means it has a very high heat capacity and it will absorb a lot of your heat. Woo! What a ride that was.
Oh man, Travis, I gotta tell you, I sure am full of some good food and good knowledge.
Oh, right you are, Billy. Me as well.
Oh, good.
And I hope you are too. I hope you've enjoyed these last few minutes with us as we explained, well, physics.
And food.
And food.
Stay classy.
That was so good. I'm sorry I messed that up. Glad we chose the candles.
This is nice. Glad we did this.
Me too.
Okay.